So first of all, we need to understand what molar mass is, okay? Molar mass is the mass of 1 mole of a substance. Okay, you probably don't really know what the term mole means, do you? Is that new for us? It's not the animal, right? We're talking about a mole of substance. It's measuring the quantity of a substance. So 1 mole, let me write this down. It'll probably come up in my slides in a little bit, but I want to put it out now. Okay, 1 mole of a substance, 1 mole of anything is equal to 6.022 times 10 to the 23rd of that thing. Okay, I'll write it in a better color. 6.022 times 10 to the 23rd of that thing. Does that number sound familiar or no? No. That's called Avogadro's number. Of course. So this amount, think of it as like a dozen, right? But a lot bigger. Okay? If I have a dozen donuts, how many do I have? 12. If I have a dozen roses, how many do I have? 12. A dozen baseballs, 12. A dozen, whatever, 12. Right? A mole is the same thing. So 1 mole of hydrogen atoms would be this many hydrogen atoms. 1 mole of oxygen atoms would be this many oxygen atoms, right? It's just a bigger amount, okay? So it's a huge quantity of things. We usually think of this number when we were talking about the number of atoms of something, okay? So a mole gives us a way to measure that quantity in more manageable numbers. So we're not always having to talk about hydrogen in terms of 10 to the 23rd atoms of hydrogen, right? Mole gives us a way to measure that in a number that makes a little bit more sense for us, okay? So what we look at with the molar mass is how much would 1 mole of a certain substance weigh. Okay, we can find the molar mass of both elements and compounds. What's the difference between an element and a compound? Right, a compound is chemically bonded elements that form something new. So an element might just be carbon, but a compound could be CO2, right? Or H2O, or whatever compound you might be thinking of. So we can calculate the molar mass of both elements and compounds. The good thing for us is that the molar mass of a single element is given to us on the periodic table. Okay, it's given to us on the periodic table. It's the same as the atomic mass. It's just on a different scale. So when we talk about the average atomic mass, we measure that in AMU, atomic mass units. When we look at the atomic mass, this is of a single atom. So we're looking at it on a very, very tiny level. Okay? So if I was looking at the atomic mass of carbon, the atomic mass of carbon is 12 AMU. That means I've got 6 protons, 6 neutrons, so together it weighs 12 AMU. But the good thing about this is that molar mass for carbon is measured in grams per mole. How many grams 1 mole of that substance weighs. But for carbon, it's also 12, right? It's the same number. It's just on a bigger scale. So this tells me if I laid out on a scale 6.022 times 10 to the 23rd carbon atoms. If I laid those on a scale, right? If I was able to individually pick out that many atoms, put them on a scale, that would be equal to 1 mole of carbon atoms. And on the scale, it would weigh 12 grams.
Why is it so specific?
This has to deal with how it was formulated and how it was calculated. So it just means that a mole of those things. Wait, you mean why is the number so specific?
Why does that have to be 6.022 times 10 to the 23rd?
When we talk about molar mass, we don't measure it in AMU. We measure it in grams per mole, because if we put a mole of carbon atoms on a scale, they would weigh 12 grams. Just like the atomic mass is 12 for carbon, okay? It's the same number, it just has different units. Okay, so calculating molar mass of an element is very, very simple. It's just looking on the periodic table. All right, when we use, I gave the example of carbon again. Okay, 12 AMU or 12 grams per mole. If we want to find the molar mass of a compound, we have to take into account the molar mass of each of the individual atoms within that compound.
Two masses and adding them together.
That's right. Right. So if I look at water or H2O, how many hydrogen atoms do I have? What's that mean? What's that 2 tell us? Does the 2 go with hydrogen or with oxygen? It goes with hydrogen. So I have 2 hydrogen atoms. And how many oxygen atoms do I have? 1 oxygen atom. So each hydrogen atom has a mass of what? 1. Okay, so I'm going to take 2 times 1 plus the mass of 1 oxygen atom, which is 16. Right, we're going to round these to whole numbers as much as we can. Okay, so I'm going to take 2 plus 16, and I'm going to get 18 grams per mole. Right? The same number as average atomic mass, but we're measuring it in grams instead of in AMU. Pretty simple, right? Let's try another one. What if I had the formula CaCO3 and I want to find the molar mass of this compound? I've got 3 different elements I have to account for. Okay? We got to start being able to locate them on the periodic table. So where's calcium at? Right over here. Right? Number 20. Its molar mass is 40. We can round that to a whole number. Plus the molar mass of carbon, which is 12. Plus how many oxygen atoms? Sam, are you already done? Uh-huh. Yeah. How many oxygen atoms do we have?
16 times 3.
Good. We've got 3 of them. They each weigh 16. And so I add those up. So if you don't have your calculator out, I need you to have it out. Okay, 40 plus 12 plus 48 gives me a molar mass of 100 grams per mole. Okay, so what this value tells us is that if I were to put a mole, 6.022 times 10 to the 23rd of those molecules on a scale, it would weigh 100 grams. Okay, that's what it's saying. If I picked out individually 6.02 times 10 to the 23rd of those molecules and I put them on the scale, it would weigh 100 grams. Okay, I want you to get used to that unit, grams per mole. Okay, it's this many grams per 1 mole. Right, that's what it's telling us. Sometimes we have compounds that have parentheses in them. We haven't seen many of these yet, but sometimes we have compounds with parentheses and there's a subscript outside of the parentheses. Okay? What it would look like is this. Right, we might have a compound that's written like that. Okay, it's called magnesium nitrate. What that says is we need 2 of these full nitrate molecules paired with 1 magnesium. Okay, so if that is the case, the number outside the parentheses, I'll kind of write this up here, the number outside the parentheses or the subscript outside the parentheses multiplies everything inside by that number. So it's like distributed through there. It's not added, it's multiplied or distributed through there. So if I was going to look at that formula again, MgNO3 2. Okay, tell me how many magnesium atoms do I have? Just 1, right? Because this 2 does not apply all the way over here. It only applies to things in the parentheses. So I've got a magnesium atom, and what does it weigh? What's magnesium's molar mass? 24.3. We can't round that one to a whole number. Okay, that's one of the ones that we had an exception for when we were memorizing our first 20. Magnesium is not close enough to a whole number to round. Okay, so 24.3 plus how many nitrogen atoms do I have? How many nitrogen atoms? Right? There's 1 right here. If there's not a subscript written, we assume it's a 1. And then 1 times 2 is 2. So we've got 2 of them, and they each weigh what? 14. Okay, and then how many oxygen atoms do we have? 6. There's 3 per molecule, and we need 2 molecules of that. So 6 times 16. And then I do the math. If I have a molecule that is NO3, that means nitrogen with 3 oxygens bonded to it. And if I need 2 of those molecules, that would mean I have 2 nitrogens and 6 oxygens. So when we add that up, I got 148.3. What's the units for molar mass? Grams per mole, right? Grams per mole. Okay, why don't you try this one on your own? Fe2SO4 3. So here I've got 2 iron atoms. Three sulfur atoms. And how many oxygen atoms do I have? 12, not 7. And so that gives me 399.6. Good. 399.6 grams per mole. Okay, with molar mass, it's not a huge deal if you're off by just a little bit, right? It could be a rounding thing. I like to put everything in my calculator like at once. I don't like to put one thing in and then hit enter and then retype it back in. I just don't like to do that. So I like to put everything in kind of at once, and so my calculator just does the math and rounds it as it wants. But if you would have 399.8, no big deal. 399.4, not a huge deal. You know what I'm saying? So you can have a little wiggle room on that molar mass. I would prefer that that's not rounded up to 400 because I want you to keep that one not at a whole number just yet. Okay? Does that make sense? All right, I'm going to have you try a couple here on your own. Okay, so try these 3 on your own. I'll zoom it out a little bit. I think for chlorine, I keep it at 35.5. That's where I round that to. So when I've got 2 of them, that puts it at 71. But again, I don't round magnesium to a whole number. Sodium, sulfur, and oxygen can all be rounded. Nitrogen, oxygen can be rounded. All right, that's about what I had. So if you didn't have that, do you have questions that I can answer for you? For molar mass, we use the unit grams per mole. And if we're asked for atomic mass, we use the unit AMU. Otherwise, they are calculated the same. Okay, we would calculate them exactly the same way. The difference is the unit. Okay, so molar mass is grams per mole. Atomic mass is AMU. Right? Atomic mass should be easy to remember because the unit for it literally is just atomic mass unit. Right? That's what it stands for. Okay? All right, last thing I want to look at today is something called percent composition. What does composition mean? What's composition mean? Yeah, David. Bingo, right? What something is made of. So when we look at percent composition of a compound, we're going to look at this after we've calculated the molar mass, right? The molar mass allows us to calculate what percentages a compound is made of each element, okay? So you can find percent composition of elements within a compound after we've found the molar mass, okay? What a percent composition is, at its most basic form, is a comparison of the individual elements to the compound itself. Think about when you take the percentage you've got on your test, right? You compare the number you got right to the number you should have got right? And that gives you the percentage you got on the test. We're doing the same thing here. We're looking at what percentage of my compound is made up of hydrogen and what percentage of my compound is made up of nitrogen or whatever it might be. Okay, so that's what percent composition is. We're looking at what percentage of the mass is given by each of the elements. Okay, so we're going to find the percent composition of sodium and chloride in this compound, sodium chloride. Okay, so the very first step is, in any percent composition problem, is to find the molar mass of your compound. Because if I want to compare sodium's mass to the whole compound's mass, I have to know what the whole compound's mass is, right? I have to know how much the whole thing weighs. So that's what we're going to do first, is we're going to find the molar mass of sodium chloride. One sodium atom is 23. A chlorine atom is 35.5. And that gives me a molar mass of 58.5 grams per mole. Okay? So once we have that, we're going to compare the individual parts to the whole. So if I want to find the percent of sodium present in this molecule, I'm going to take the mass of sodium, 23, divided by the total. That's it. Right? We're taking the part divided by the whole. So if I'm looking at sodium, I'm taking the mass of sodium found in the compound, 23, and I'm dividing it by the total. And that's not going to come out in a percentage, it's going to come out in a decimal, right? So 23 divided by 58.5 gives me 0.393. And so what does that come out to be as a percentage? Good, 39. Let's include that decimal. So 39.3% of that compound is made up of sodium. Right? That's all it is. You guys should know how to calculate percentages. Agreed? We take the part divided by the whole and we get the percentage of sodium. But that's only one part of it. I want to know the whole percent composition. So I need to do the same thing for chlorine. So if I find the percent of chlorine, I'm going to take chlorine's mass in the compound, 35.5, and take it divided by the total, 58.5, and I get 60.7%. So 60.7% chlorine. What should my percentages add up to be? 100, right? Theoretically, I could have just taken 100 minus my sodium percentage and gotten my chlorine percent also, right? The problem with doing it that way is if I miscalculated sodium, then now I miscalculated both, right? But does that make sense? If I only have two types of elements and I find the percent of my first, I could take 100% minus that one and get the percent of my second. But if I miscalculated my first one, then I'm off on both. Okay, so the way to check your answers here to make sure that you did everything right is to add these up and make sure they add up to 100. Sorry, I didn't realize I was going off the bottom of the page. Okay, add those percentages up and make sure they come up to 100 or very, very close to 100. Okay, why don't you try this one on your own? Find the percent composition of calcium nitrate. I don't want the percent of just calcium. I want the percent composition. So I want everything. When it asks for composition, you'll do every element. If it asks for just a single element, then you only have to do that element. Part divided by the whole. Okay, so I'll write it a little bit bigger up here. It's CaO3. NO3 2. That's what you want the percent composition of. CaNO3 2. Right, so the question that was asked was, if I'm taking nitrogen, part divided by the whole, I'm not just taking 14 divided by my total, because in the compound, nitrogen didn't just weigh 14. There was 2 of them, so it weighed 28, right? So if we would have done 14 and just 16 for oxygen, our percentages would not have added us up to 100. So right now, if I add up what I have, that gives me 99.9, right? Close enough. Okay. You got 99 flat. I would encourage you to keep the 10th place on that percentage, but that's probably why. Okay?
I did hold on.
That's fine. Not the end of the world, but I would probably encourage you to keep a 10th place there.